series. We're going to start by reviewing what a function is. A function is just a relationship where you have an input and a single output. And some functions are defined using a mathematical expression. This one is defined using a mathematical expression. It's y equals x squared. Not all functions need a mathematical expression to define them. Each of these functions are based on this contour that for this animal down here, this drawing of the animal. The contour starts here, so that's point 1, 2, 3, and there's 1,000 points all the way around this. And they come back here. And for each input, and the inputs are actually the position on the contour, so you got the first position, the second position, third position, and so forth. So the first position for function A, its output is the x-coordinate, and the x-coordinate is the first x-coordinate. The second position is the second x-coordinate, and so forth. So this function here is made up of all of the x-coordinates of this contour drawing. Note that the first point on this function, or the first input for this, its output is equal to the value of the last output. So the first output is equal to the last output. Same with this one. Now this one is different. This is based on the y-coordinates, but it's still for each point along the contour. So point 1 is going to be the first y-coordinate, and then the second y-coordinate, and so forth, all the way to 1,000, because there happen to be 1,000 points. So this is also the same thing, where the output here for the very first point on the contour is equal to the output here, which is the very last point on that contour. Okay, now we want to talk about a cyclic function. And a cyclic function is just a function that repeats, or can be made in such a way that it appears to repeat. Now this function here is just function A from the previous page. And as we said before, its first point, its first output, is equal to its last output value. And this makes it easy to turn into a cyclic function, because all we do is append or concatenate a bunch of function A's to each other, and we get a function that repeats itself. So you can think of a function like function A, where the first output is equal to the last output. You can think of those as cyclic functions simply because they're easy to make into cyclic functions. So function A is a cyclic function, as is function B, because they have that same property, where the input, the first output is equal to the last output in each one of these functions. Okay, so now the Fourier series, any cyclic function can be approximated by summing up the right set of sine and cosine functions. Sine and cosine, well, this is actually a distorted circle. So it looks like an ellipse, but it's not. It's actually a circle. It's the unit circle. The y-coordinates of this unit circle are the sine functions, and the x-coordinates turn out to be the cosine function. And so this is analogous to the drawing we have of our animal in the previous slides. Okay, so now I have the right set of functions over here. These are the functions that, when added together, will eventually result in a very good approximation of function A. Now this is function A, but it's just stretched a bit. It's scaled a little bit differently, but it really is the same function. And so we're adding these functions together, and by adding, we're adding all the corresponding points. So I add this function to this function. By adding all the corresponding points, there's 1,000 points on each one of these functions. And when I add this one to this one, I get this one. When I add all 3 of them together, I get this one. When I add all of these together, and so forth. When I add all 5 of these together, I get this one. And now we're adding everything. So we've got a total of 10 functions, 5 on the previous page and 5 here. When you add all of them together, we've got this one, which looks more and more like function A does. Now, how do we get to right? Well, our raw material is actually integer valued frequencies of the sine and cosine function. So this here is the sine function when the frequency is 1, sine function when frequency is 2, all the way down to sine function when the frequency is 8. Here's cosine function, frequency of 1. and here's cosine function frequency of 8. Now we actually need, to get this to work correctly, in theory, Fourier series needs all of the sine and cosine function with frequencies 1, 2, 3 up through infinity, and you add all of those together to get your final function after you've done some manipulating of each of the functions. But of course you can't have an infinite number of functions, so it turns out that you have to use a subset, and we got for what we did, we got it to work quite well with 300, by summing up 300 functions. In other words, we had sine and cosine for 300, for frequencies 1 to 300. Okay, so again, this is repeating what we already showed, except notice that what we're doing, we manipulate the sine and cosine functions by changing their height. And so if you notice how the heights here vary as we go down, the amplitudes vary. Okay, so this is really, we already saw this. Okay, so now how do we get the amplitudes to vary? What do? Well, we need to get a number to multiply each one of these functions by, which will become the coefficient that we multiply the functions by. And to do this, we take the inner product with a sine function or a cosine function and the original target function. So our target function, this is function A, and we're getting the inner product. We get the inner product between this and this. The inner product is, well, remember these have 1,000 points on them in this case. And so for each one of these individual points, we multiply it with the corresponding points here, and that's going to give us 1,000 products. We add those together, and that sum becomes the coefficient that we put in front of this particular function. So the first function we're going to have is a sine function with a coefficient multiplying that whole function by whatever the result is of the inner product. And we do it again we do it for the sine and the cosine function. We're just showing you the sine functions here. This is for frequency 2, frequency 3. Okay, and it would go to, well, to get ours to work, we needed to go through frequency 300. Okay, now what does this calculation mean? What is the inner product telling us? Well, the inner product tells us the similarity between those two functions. And the larger that value is, the larger that inner product value is, the more alike these functions are. And it's similar, in fact, it's exactly the same as the correlation calculation you see in statistics, because this is an inner product. They're doing some scaling here, so this value is always between +1 and -1, but it's still the same idea. The closer you are to -1 or +1, the more alike the functions are, the more they behave in the same sorts of way, in similar ways, the closer they are to 1. So if you have two different sets of data and you get the correlation between them, if R happens to be very close to 1, it means those data will behave the same. And if it happens to be -1, they still behave very much the same. It's just that their directions are opposite of each other, but they're still very similar. And so the inner product of two functions is a measure of how similar the two functions are. Okay, so now all of this adding and all of this multiplying and all of this work seems like an awful lot of work to do to just get a copy of a function that we really already have. And so what's the point of doing this? Well, it turns out to begin with, it can be a little bit entertaining, and we'll show you how it can be entertaining. Okay, so what we've got here, these are the x and y axes of this same drawing we've been looking at. And remember, you just put the x and y axes together and you wind up with this. Well, here's the first approximation with the first frequency for the x-axis, and here's the first approximation for the first frequency with the y-axis. Now, if we put these together, so this becomes the y-axis of this ellipse, this becomes the x-axis, this here becomes the x-axis of the ellipse, this becomes the y-axis of the ellipse, and we get this ellipse, this shape here. And it captures the direction of this drawing. And as we do the same thing for each one of these. So here the red, when we take the red and make an x-axis and a y-axis, put that together, we get this shape here. Now it's looking a little bit more like a horse. And so this is frequency 4. Now we're at frequency 5, and we're beginning to look something like an animal. We're all the way down here to frequency 8, and it's really beginning to take on the shape of an animal. And so what's happening is, as we get more and more frequencies involved with the summations and all that, it looks more and more like our target shape. So now we're going to jump up to frequency 21, and it's beginning to look a lot like this animal over here. We're missing ears. Okay, so now we're jumping up to 45, frequency 45 through 48, and we're getting some ears here, but it's not perfect yet. So now we're going to jump all the way down to the end. And so now we got frequency 297, frequency 300, and now these almost a perfect match. And if you notice, the red is sitting right on top of what was of the black one, so that's why you don't see the black one anymore for each one of these. So this is very good. Now we can make a little animation out of this, and we'll see that next. Very important applications of the Fourier series. An interesting historical one took place during the Cold War. Kennedy and Khrushchev made a treaty that was the nuclear test ban treaty, which meant that nuclear tests could no longer take place above ground. They had to take place underground. And that's really good, except it makes it very difficult to know when your opponent is doing an atomic test. Now you can actually get the rumbles from an atomic test and record them using a seismograph. But the output from a seismograph for a nuke test looks very much like the output from a seismograph for an earthquake. And so there was no way to tell which was which. And so we weren't sure when the Soviet Union was setting off a nuke test. But it turns out that if you take this output from a seismograph, which is just a function, and break it down into its Fourier series components, the atomic tests have frequencies that are not seen in the earthquake, and vice versa. So they're missing they have different components of frequency, of sine cosine frequencies in their breakdown, when they break them down. So it's a very important application, and it's also used for removing noise from audio recordings. It can also be used for removing noise from video recordings. It's also used in radar detection. So I don't think it's a stretch to say that some of the very most important applications of sine and cosine have to do with Fourier series.